Hello, everyone. Welcome to an instruction set for the web here at Devoxx on the Modern Web track. Thank you very much to the conference organizers for having me. I actually just came last week from our Angular Connect conference in London, so I'm really excited to be here in Belgium this week for Devoxx. When I was sketching out what this talk would look like a couple months ago, I decided I wanted to talk about Angular's new instruction set that we're designing for our next renderer. But as the talk started to come together over the last couple weeks, I realized there was another piece to it as well. So while this is a talk about our instruction set, it's also really an introduction to some of the challenges of designing a modern web framework, and a case study of the particular design that we decided to go with. And while some of the things we're doing with Angular Ivy are really only applicable to a framework, many of the techniques that we're using are relevant to any web code base, especially something like a library that's intended to be used by lots of web apps. And so it's my hope that from this talk, you'll take away two things. And the first is that, kind of surprise, web development is complicated. And that's one of the many reasons you see tooling becoming more and more important in the web ecosystem. My first ever job in the industry, I worked for a company that edited their code base by FTPing files down from the production web server, right, typing out their changes in the editor, and then FTPing those files back up to the production server and refreshing the page to see if their changes worked. My first day on the job, I introduced them to this little thing called Git. It blew their minds. They had no idea that this was possible. But in a world today of evergreen browsers and living standards, polyfills and CDNs, tooling is what's helping us actually keep up with the ever-changing ecosystem. And the second thing I hope you take away is that good design, especially of something like a library, needs to take this tooling into account. If you consider how the code is built, how it's packaged and optimized and deployed, if you work with the tooling, you can achieve a much better result. So this talk is largely the story of how Angular is factoring in the tooling of the web ecosystem into our latest update to our framework. Before we get started, though, I should introduce myself. I'm Alex Rickabaugh. I've been a software engineer at Google now for about 8 years. In the last roughly 3.5, I've been a member of the Angular core team there. And in my time on Angular, I've worked on a couple different parts of the framework. I worked on our HTTP client, which is used to interact with backend services. As part of our effort to support progressive web apps, I built our service worker. And these days, I maintain Angular's compiler. And I've been working on updating the compiler as part of our Ivy effort. So here is the plan for roughly the next 45 minutes or so. First, I'll give a quick introduction to Angular. How many people in the room are Angular users? All right, OK, it'll be a very quick introduction because it's most of you. So if you haven't used the framework before, don't worry, I'll cover the basics. Then I'm going to go through some of the challenges, the things that make development of a framework like Angular complicated. And that's going to be context that will kind of help you understand some of the decisions we're making for Ivy. And finally, we'll look at Ivy itself and see how it works internally and why we chose to do it the way that we did. So Angular is a modern web framework. It's one of several that developers typically choose from these days. It's been around for a while. The version 1 product was AngularJS, and that actually came out over 8 years ago in 2010. And around 2 years ago, we underwent a major rewrite, and we released the version 2.0 we called Angular. We dropped the JS, partly because we rewrote in TypeScript. TypeScript is an emerging language from Microsoft. It aims to add static types to modern JavaScript code. If you write JavaScript and you've never used TypeScript, I cannot recommend that you try it enough. When I go around to conferences like this and I talk to our Angular users, almost always they tell me one of the things they love most about the framework is using TypeScript. And there are a lot of reasons for that. In a small code base, TypeScript really helps you keep organized still. It has really good type inference, so it doesn't end up being as much of a burden as some other static typing systems. You can generally omit types when the compiler can figure them out, and you only really end up typing the kind of API boundaries. TypeScript is also a really good transpiler. You write your code against a syntax that's not really supported in modern browsers, and so TypeScript takes care of generating code from that will actually run in the older browsers like Internet Explorer 9. But when you have a large code base with dozens to hundreds of engineers and thousands of files, that's where it really starts to shine. And at Google, we have thousands of engineers writing code in TypeScript. We have hundreds and hundreds of applications running on it. And the Angular team is actually responsible for updating all of those projects whenever we make changes that require it. For example, when we moved to the new version of Rx that uses .pipe instead of operators on the prototype, the Angular team was the one responsible for pushing that change out to every project in Google using Rx. And we would not have been able to do that without the refactoring support that TypeScript gives us. So as a framework, Angular is built on a number of different principles. Like most web frameworks today, it allows UIs to be built through composing reusable components. You typically write those components in HTML with templates that describe the view and controller classes which provide the logic for that view. We have framework support for things like dependency injection, for making your code more modular and testable, as well as things like lazy loading. So I'm sorry, like most of you are Angular users, but if you haven't actually used Angular, this is kind of what it looks like. This is an Angular component. We're actually using an extension of JavaScript, a new proposed standard for decorators. So we use decorators to indicate that classes have certain special behavior, right, or meaning to the framework. So the @component decorator creates a component. The object being passed to it is metadata about that component, things like what is the HTML element that it's created with, and where to find the template for the component. The fields of the component class also serve another purpose. They are available in the template for binding. So here's what an example template might look like. This is normal HTML, except for note we have this double curly brace country here. What this is doing is telling Angular we want to take the value of the country field on the component class and insert it into the text of this paragraph tag when we're rendering it out. And Angular actually keeps track of these things. They're called bindings. And we notice whenever the country field changes, for example, and we take care of updating the view for you. We call that feature change detection. TypeScript also supports a control flow, templates also support a control flow syntax through these things we call directives. So here we have the ngIf directive, and what it's doing is showing or hiding this conference schedule section based on the value of an expression. And on this conference schedule element, we have a binding to the data property indicated with square brackets. And that's telling Angular we want to pass the schedule field of our component class into this conference schedule element so that it can work with the data in the schedule. And here's an example of what that component might look like. On the other side of that binding, we have a conference schedule component which has an @input decorator on this data property. And that's telling Angular that this data field represents a public property of the component, something that a consumer might provide a value for. And Angular will take care of updating the value of this field whenever the consumer provides a different value. And as I mentioned earlier, Angular supports dependency injection, where things like services can be injected into the components and other types that you create in a modular and testable fashion. And so here's an example of one of these services. It's a schedule service for retrieving the conference schedule. A real implementation of this might go to the web through an HTTP call to look at, get the current schedule from a server. Here it's just hard-coded. But note we also have an @injectable annotation here. And that's telling Angular that this type should be created through dependency injection. So in our original Devoxx hello component, accessing the service is as simple as adding a parameter to the constructor of this class, saying we take this service when we're created. And once it's injected, it can be used to retrieve the current schedule and assign it to this property where it gets pushed out to the view. The Angular ecosystem extends far beyond this framework and its immediate capabilities. Under our umbrella, we have testing tools, we have IDE integration, we have developer tools, we have a material design suite of high-quality components that use the material design visual specification. If you're not using material design visuals in your application, we have a component development kit that you can use to build your own components based on some of the work we've done. And we also have a command line tool, our CLI, which, among other things, can scaffold applications and build them using the best practices that we've derived. And in fact, our CLI allows us to kind of change over time how Angular applications are built if the ecosystem evolves or if the framework evolves. We have an incredibly active community. We have millions of developers around the world, nearly 1,000 meetups worldwide. And at Google alone, we have several hundred Angular applications, and that number grows every single day. And that brings us to the second part of this talk, a quick tour of the complexity in the JavaScript ecosystem. Because it used to be that when you were using a JavaScript library like AngularJS, you would do so by inserting a script tag on your page. Sometimes web programming back then kind of felt like cutting and pasting applications together by assembling little different snippets of scripts. That hasn't been the case for a while now, right? Web development has gotten a lot more complicated. We've moved from a script-based world to an ecosystem with package managers and transpilers and compilers and bundlers and all this other assorted tooling. And the power of that tooling is incredible, but so is the kind of complexity that it introduces that we have to deal with. So I want to talk a little bit about this complexity that we, as framework authors, deal with to give you the best context for understanding how Ivy was put together. And specifically, I want to talk about the way that code is packaged for execution in the browser. How do we go from code that you write in the IDE to the code that actually executes on our users' machines? Right? And hopefully there's a better answer here than FTP. In a modern JavaScript project, you'll probably be writing code, if not in TypeScript, then at least in one of the more modern JavaScript standards like ECMAScript 2017 or something like that. And so you probably have a transpiler because not all browsers can run that just yet natively. Most applications also don't deploy to modern ES modules. Browsers still tend not to handle that well either. And so you probably have a packer, something that bundles the code together in a way that can be loaded in an older browser. You probably have a loader to pull dependencies off of NPM. And finally, this code bundle gets optimized and then split up into different parts for lazy loading. And only then does it actually run in the browser. So there's a lot that happens between when we write a class in our IDE and the code that actually executes for that class in the browser. And it's the last part of this process that I want to focus on, this trio of bundling, optimizing, and splitting. On the surface, those seem kind of like separate sequential operations, but in fact, they're very interrelated. It's impossible to optimize an application, for example, until you have all the code bundled together in one place. Only then can you do things like rename properties across the entire application, or try to figure out which code isn't used at runtime and remove it. And you can't split up code for lazy loading unless your bundler also gives you a way to link that code back together again when it's all loaded in the browser. So these three operations are so entwined that they actually happen most often in the same tool. In the Angular CLI's case, that's Webpack. We use Webpack with a variety of plugins to perform all of these steps as part of our production build process. So optimization is a critical part of the JavaScript bundling process. Our users don't conveniently live down the street from our data centers with nice big fiber connections running to their computers, right? They're on mobile, they have wireless connections, they have congested connections. There's all kinds of latency between our servers and their screens. And this means that producing small, optimized JavaScript bundles is essential for creating a good user experience. And the optimization of tree shaking is one of the main ways we do that. Tree shaking has a couple different names. Some people call it dead code elimination. Other people argue that no, it's called live code inclusion. They're all just different ways of talking about the same optimization. In tree shaking, the optimization tool is scanning a production bundle and trying to prove that certain parts of the code, certain functions, have no effect at runtime. Either because they're not called at all, they're not referenced, or because they are referenced, but they don't actually have any real runtime effect. They don't do anything. And if it can prove that, then it can actually eliminate that code from the bundle. And quite often, eliminating one function removes the last remaining references to other functions, and they become eligible for tree shaking as well. And the first time I heard this, I thought, oh, that's interesting, but it can't actually be that big of a deal. Because most application code that gets written tends to be used anyway, right? I'm not in the habit of as an application developer of writing code that I don't actually use on my app. I have too much work to do to be that inefficient. So why is tree shaking important? Why is it something that you should do? And it really matters as an optimization because of libraries. Right? We write code in our applications, but we also reference code from libraries. We import things from material design, for example, or Moment.js for working with dates and times. And I don't know if you know this, but when you import code with an import statement from a library, the spec says that the entire library must be included in your bundle because it might have these kinds of side effects. It's the tree shaker's job to remove that inefficiency by understanding the code enough to prove that you don't actually need all of it. That if you're only using a material button, you can remove the code from material side nav because it can't actually have any runtime effect. And in the JavaScript ecosystem today, there are a few tools which have emerged as capable tree shakers. There's Rollup for ES 2015 code. It performs what it calls live code inclusion, where it eliminates declarations that don't actually get referenced. Webpack launched tree shaking in its version 2, largely inspired by how Rollup works. One that I was surprised to find on this list is Uglify. Uglify is a venerable JavaScript compressor. Its job is to make your bundles smaller. And it does that by applying a variety of transformations, renaming properties, removing white spaces, making your code look very unintelligible. But one of the things it can do is dead code elimination. And the last tool I want to mention is Google's Closure compiler, only really because it actually achieves the best results of any optimizer, provided you opt into its requirements. It actually requires you to write your JavaScript code in a very kind of structured, specific way. Now, applications, right, application developers, gain the benefits of tree shaking by applying one of those tools. But it only works if the library authors have gone through pains to ensure that their library code can in fact be tree shaken away. It's really easy to fall into a number of anti-patterns where if you do things in the wrong way, you completely defeat the optimizer and nothing in your library can be removed. And by far the most common of these anti-patterns is this thing called the conditional reference. And we've all written code that looks kind of like this. In this example, we have a shape variable. And shapes have a type. So a shape is either a square or a circle. So if the type of the shape is a circle, then we call the drawCircle function, and we know the shape has a radius. If it's a square, then we call drawSquare, right? And we know it has an edge length. This is nice object-oriented code. TypeScript even knows how to type check this. You can teach it that shapes which have type circle have radiuses, and shapes which have type square have edge lengths. The problem is, if we ship this code in a library, it might end up being used in an application that only ever wants to draw squares. And that's perfectly valid, right? Our library is good at drawing squares. But a tree shaker looks at this code and doesn't know that. It doesn't know that the application never constructs an object that has type circle. It has to assume that either of these branches is valid at runtime. And so it has to retain them both and retain the draw circle function as a result. So the circle functionality will never be removable from our library if we write our code like this. And there are a few other patterns that come up that kind of defeat tree shaking, but this is the one that I find is most common. So we set about designing Angular Ivy, taking into consideration things like that. But to really understand how Ivy works and how it's different from Angular that came before it, we have to look at how the current rendering architecture in Angular works under the hood. There are three parts to any Angular application. You have the application code itself, right? The components, the templates, the services that you write. You have the framework itself, right? The code you import from Angular. But you also have the code generated by our compiler. Our compiler runs on your templates and reads them and generates these things called ngFactory files. And if the component class represents the controller for the view, the ngFactory file represents the template itself, the kind of DOM structure of the view. And that generated code works together with our framework to both render and update the views in your application. And together we call the framework and the compiler that generates that code a renderer. Angular's current renderer is known as the View Engine. It debuted in Angular 4.0. And its design was largely based around making the generated ngFactory files as small and lightweight as possible. And we largely achieved that. And I'll show you how this works. So we're going to look at this example template and see how it's compiled across Angular with View Engine and Angular with Ivy. And this template is pretty simple. It has a couple elements. It has a data binding to title, and it has a child component here being rendered with an ngIf. And if you take that template and feed it into our current compiler, you get something that looks like this. I did this. I dug around through the ngFactory file and pulled out this section which relates to actually rendering the template. And what this is a declarative structure. View Engine creates a data structure which describes the template to Angular. And then we have a piece at runtime, our interpreter, which traverses this data structure in order to create DOM nodes or update them. And there's a lot of magic numbers and a lot of nulls running around. But I've added some arrows here to kind of explain what's happening. So the white arrows indicate the HTML elements being created. You can kind of see where they end up in this array here on the right, the div and the span. The top red arrow shows where the template, where the binding goes, right? The text node that will receive the title. And the bottom red arrow shows what happens to that ngIf for control flow. In general, this declarative structure ended up being really compact. It was a big win when we shipped it in Angular 4.0. But as we've continued building our framework, we've started to run into some architectural issues with this. There are some features that we just have not been able to support because it just doesn't work to fit them into the way the View Engine works. As we've also expanded Angular to take on more embedded use cases, we've encountered situations where our code does not optimize nearly as well as we wanted it to. And for these and a few other reasons, we undertook a project to redesign how rendering works in Angular for the third time. We called the new renderer Angular Ivy. Ivy had a few different design goals, but the overarching theme is that it's a simplification of how Angular works internally. With Ivy, we've been able to remove a lot of the complexity from our framework, from how we compile applications, to how libraries are structured and deployed on NPM, to how those pieces interact at runtime when they're finally all loaded together. And simplification is a good goal in and of itself. It also tends to have a lot of follow-on effects. It has a lot of kind of downstream impacts that you don't necessarily anticipate when you start the project. And besides making Angular simpler to use and easier to understand, we had a couple other goals that we set for ourselves when designing Ivy. And the first one, and the one I really want to focus on today, is optimizability. We wanted to make Angular code, both the code in our framework and the code we generate for your applications, far more optimizable by the current suite of JavaScript tooling. We wanted to take full advantage of the best the ecosystem has to offer. We also wanted to make compilation incremental, which has a twofold benefit. It speeds up compiles, and it also makes it easier to ship libraries because you don't have such complex requirements around metadata. And lastly, we wanted to make sure while we were doing all of this that the new renderer would be a solid, flexible technical foundation for Angular to deliver all of the features that we wanted to do going forwards. So let's take a closer look at Ivy and see how this new architecture achieves these goals, in particular, how it's optimizable. The central idea in Ivy is that each Angular decorator, instead of resulting in an ng factory file being generated somewhere else, gets compiled to a static field on the class itself. So the @component decorator gets compiled to a static ng component def field on the decorated class. @directive, same thing, ng directive def. @injectable, ng injectable def. So we've taken the code that used to live apart from the components in these separate ng factory files and moved it onto the component class itself. And here's what this looks like in practice. On the left, we have a root component. It has our same example template from before, with the div and the span and the binding. And on the right is the output of what the Angular compiler does today if you tell it to produce Ivy code. Our component class has been compiled by by TypeScript normally, but what Angular has done is added this ng component def. In fact, you can think of our compiler as simply translating decorators into static fields. And this field contains some information that's used by the Angular runtime to render this component. Things like its selector and the fact that it uses two directives, the child component and ngIf. And it also has, down at the bottom, a template function, which is responsible for rendering the component to the DOM and updating it through change detection. And this template function looks like this. Right away, you'll notice a couple different things about it. It's no longer declarative. Ivy templates are imperative code. It's also pretty short. It contains direct calls to create the elements. We have a call for element start of a div, element start of the span, element end calls at the bottom for those that match up. We can see where our text node is. We can see the ngIf being added. And another thing I'd like to point out is that unlike with the view engine, I've actually been able to fit the code for change detection here. So the top if branch is responsible for creating the template in the DOM. The bottom branch of the if is responsible for running change detection. So we have two binding operations here, a text binding for the title, and our other binding to an element property, which is actually our ngIf condition. So instead of a single monolithic template interpreter, like we had in the view engine, in Ivy we've broken up the Angular runtime into a set of individual rendering operations that we call our instruction set. It's almost, you can think of it as an assembly language that Angular applications get compiled to. A template gets compiled to two sequences of these instructions, one to create it in the DOM, and the other to change detect it. And this instruction set is pretty comprehensive. It covers things like internationalization, data binding, content projection, as well as the kind of more normal things like DOM manipulation. So as an example, let's look at how dependency injection gets rendered to a sequence of Ivy instructions. So here's our example service class that we're going to use. This is an authentication guard for our router, and it injects a couple things. It injects the router, it injects the HTTP client, and this configuration object using an @inject. And you might imagine this guard would have logic like this. When the user tries to navigate to a particular route, it'll check the configuration to see what permissions are required for that route. It'll then use the HTTP client to ask the server, does the user have those permissions? And if the user doesn't, it'll use the router to navigate away. What Ivy's going to do is compile this @injectable decorator to an ng injectable def field. Let's see what that looks like. So we get an ng injectable def with a factory function. And this factory function is responsible for creating instances of this service. And it does that in two steps. The first step is that it calls Ivy's inject instruction for each dependency of the service to get an instance of the dependency, and then it just calls the constructor with those injected arguments. This is actually how my mental model of dependency injection works, right? You first inject the parameters, and then you call a constructor. And one thing to note here is if this service had no dependencies, you wouldn't end up actually writing a reference to the inject instruction at all. The factory function would simply be new off guard, right? Open paren, close paren. That's not an accident, as we'll see. So let's talk about the benefits of this approach and how it helps make Ivy applications more optimizable. Ivy lets us leverage, as I mentioned, a growing suite of optimization tools in the ecosystem. And in particular, it generates code which is very tree shakeable. It's helping us move Angular more towards a model where if you don't use a feature of the framework, you don't pay the cost of including that feature in your bundle. Tree shaking lets us get there. The Ivy runtime was designed from the ground up to be tree shaken. That's why we've broken it up into separate functions, separate instructions. If you don't use internationalization in your application, your template gets compiled, and the compiled code doesn't reference the internationalization instructions. The tree shaker can see that and will remove those instructions from your bundle. If you don't use SVG elements directly in Angular templates, which is something we support, your template will not include references to SVG-related instructions, and they can be removed from your bundle by the tree shaker. And this works across the entire framework. Core concepts like dependency injection are also tree shakeable. If you don't use DI in your Angular applications, if you don't have services that you inject, then you can actually write an application without an application injector. And that code can be removed from your bundle. And this is a big improvement over the View Engine runtime. It was one of the major factors that kind of led the Ivy design. In the View Engine, remember, templates were compiled to declarative data structures. And they were interpreted at runtime by an interpreter. And we made that interpreter as small and as optimal as we could. But at the end of the day, it still had to be ready to handle whatever template you handed to it and whatever features of Angular that template used. It was impossible to tree shake. And that's because the interpreter was essentially one giant conditional block. Right? If you're using content projection, if you're projecting content into your template, here's the code to support that. If you're using internationalization, here's the code to support that, etc. There are other areas of the framework where tree shaking becomes difficult. One in particular is this pattern of dynamic component instantiation. So this often comes up when you want to insert a component into some part of your view, but you don't actually know until runtime which component that's going to be. And this can happen, for example, if you have things like overlays or tooltips or modal dialogues. And if you've never done this in Angular, the way it works is you first get a view container ref, which is a reference to the location in the DOM where you want to insert the component. But you can't insert it with a component type directly. You need to get a hold of the component's factory. And you do that with this thing called the ComponentFactoryResolver. And once you do that, then you get the factory, you give it to the view container ref, and it gets inserted in the DOM. The trouble is that this ComponentFactoryResolver is essentially a giant map. And it's a map from component type to the factory that we've compiled for that component. And the tree shaker can't see through this. It doesn't know which component types you're going to look up in this map ahead of time. And so it has no choice but to include the entire map, all of the component types and all of the factories. You can't tree shake the map or anything in it. And Ivy avoids this problem entirely by avoiding having the map in the first place. In Ivy, as I said, we've taken what used to be in the ng factory and moved it to a static field on the component. So if you have the component, you already have a reference to the factory. You don't need to go through any map to get there. And all of this focus on making every aspect of the framework tree shakeable has paid off in a really big way. If you take a simple Hello World Angular application in Ivy, you tree shake it, you minify it, and you compress it, you end up with a bundle that's about 4.5 kilobytes. And that's not an exact number. It tends to go up and down as we work on, Ivy's not done yet. But we're pretty happy with the ballpark that we're in. And a lot of people, when they hear this, tell me, oh, well, that's cool, but my application is significantly more complicated than Hello World. So I don't think that applies to me. Right? Isn't that kind of a useless measurement? And that is true. There are most applications are not quite that simple. But there are two very important reasons why we care a lot about this number. The first is that it gives us a really good metric for how tree shakeable we actually are. It's really easy when you're developing a framework feature to think, okay, most applications are going to use content projection. So it's okay if content projection is not actually removable from most bundles. And that might be true, but if you do this for every feature of your framework, or your library if you're writing a library, then at the end of the day, you'll end up with something where nothing is tree shakeable. So focusing on the hello world size keeps us honest as framework authors. It helps us ensure that every part of Ivy can be optimized away if need be. And the second is that this hello world use case is actually representative of some of the things we're trying to do with Angular. So we have this feature called Angular Elements, where you want to generate a custom element for an Angular component and include it in an application that might not even be Angular. And when you do this, you really want that custom element bundle to be small and efficiently loaded. And Ivy's helping us get there. A lot of the design patterns that we've used to make the Ivy code tree shake well are very applicable to other libraries that have similar goals. Avoid conditional references. Right? Avoid code where functions or behaviors are invoked only if there's a condition, especially if you're not sure that condition will be true for all applications using your library. That alone goes a long way towards helping the tree shaker work. Also, avoid introducing these kind of global maps, right, from one type to another. Instead, try to find a way to put a reference to the second type on the first. And while there's been a significant focus in Ivy on kind of build time optimization, things like tree shaking, there's another optimizer at work in an Angular application that we've focused on as well. And that is the JIT optimizer that runs in the JavaScript VM in the browser. And the JIT's job is to generate efficient machine code for functions that are executed repeatedly, instead of kind of the slower types of interpretation that JavaScript VMs do when you start running code. And we expect a lot of our Ivy instructions will fall in this category of functions that are called in very tight loops. If you're rendering kind of large or complex views, it's not impossible for Ivy instructions to be called many, many hundreds of times per second. And one of the things that can actually defeat the jitter is this concept of something which is monomorphic. Monomorphic means same-shaped. And I'll show you how this works and how it can cause problems for optimizing JavaScript code in the VM. So let's suppose that we have name objects. And name objects have a first name and a last name. This is actually one of those assumptions that people think is true about names, but actually isn't. But it's good enough for our purposes. And let's say we have a function that works with names called logname. And logname takes in a name object, and it prints out the first name, and it prints out the last name. Right? Easy. What kind of code will the JIT generate to optimize this function? And the answer is that it depends on the types of names that the jitter sees being passed to this function as it runs in the browser. If there's only ever one shape of name that gets passed through, and we say if the name object is monomorphic, then the jitter can generate really efficient code for this, because it can assume that the name has a certain shape, a certain layout in memory. It can write direct memory accesses to read the first and last properties. If there are several different kinds of names coming through, several different shapes, then the jitter isn't so lucky. It has to write conditional code to check, is the name of this shape? And I'll show you what I mean by shape in a second. Is the name of this shape? If so, I can reference the memory locations for first and last here. If it's of a different shape, they're in somewhere else. And if there are too many different shapes of name coming through, then the jitter just gives up entirely. And it relies on much slower methods of property access. So how can you have differently shaped names? here's an example. We have two calls to log name here with two different name objects being passed through, both of which have a first and a last property. And the one on the left has only those properties. The one on the right also has a middle name. Now, our log name function doesn't read the middle name at all. It doesn't care if that property is there. But because it's there, these two objects have different layouts in memory. The last name and the first name property may be in different locations. And so when the jitter is trying to generate machine code for the log name function, it has to take into account that not all objects, not all names that come through will have the first and last properties in the same place. How many shapes are there here? These are still two different name-shaped objects. Any testing framework would consider these equal, right? They have the same fields. Those fields have the same value. But the jitter actually cares that the order is different. So if you have the same fields in different order, those are differently shaped objects. This kind of thing only really matters for functions that are called in what we call hot code, right? Code that executes repeatedly in very tight loops. In an IV, our instructions are kind of fall into that category. They can be executed a lot of times if you have a complex view. And it's really important for overall performance of the JavaScript jitter to be able to optimize them. And so we pay a lot of attention to this kind of thing. And we take special care in our code base to ensure that our objects have the same shapes, right? And if there's a case where we can't do that, for example, if the object's coming from the user and we don't know what shape the user created it in, then we take care to cache reading that property so that we're not doing it over and over and over again every time we want to look at the element. So to fix our little name example, one thing we could do is to have one function, one place in the code where name objects are created. And TypeScript can actually help here, right? If this function is the only thing that can ever return you a name type, construct one, then you can guarantee that all names were created here, and this function can take care to create them always with the same shape. And if you do that, then function calls which use this name can be monomorphic. And that's exactly how Ivy implements these definition properties, the static properties on classes. So remember this example, right? The auth guard on the left. On the right is how the static property gets created. And you can actually see here it's created by calling this define injectable function. Define injectable is the only function in Angular which will create an injectable def. And therefore we know that all ng injectable def static fields have the same shape. Right? So the IV instructions that operate on that can be jitted very efficiently. So IV is designed to be fully optimizable by the current suite of JavaScript tooling. But that tooling is not static. There are new bundlers and new optimizers being written every day. Sometimes it feels like literally every day. There are also some optimizations which some of the more advanced optimizers can do, but which haven't made their way into the broader ecosystem yet. Closure Compiler in particular can do one of these things. It goes by the name of cross-module code motion. And what this means is if you have an ES module and you're referencing it from a lazy loaded context, you can actually move only the functions from this module that are referenced lazily into the lazy loaded bundle itself. Normally, optimizers can't split up a module. They'll move the entire module or not at all. And this is something that really could help the ecosystem. And when other optimizers do gain this benefit, do gain this capability, Ivy will be ready. So in summary, Ivy is a significant refactoring that aims to simplify much of Angular's internal complexity. By removing the need for ng factory files, we've simplified our bootstrapping story, we make lazy loading easier, we get rid of a frequent user stumbling block. But we've also made Angular work much more in concert with the optimization tools in the ecosystem for things like tree shaking, and also with the JITs that run in browsers. Our granular instruction set also helps to make templates, applications, and the entire framework more tree shakeable. By switching from global to incremental compilation, we're also making builds faster. We're simplifying the way libraries are packaged, which has been a long-standing pain point. And it turns out that this instruction set that we've written is actually the perfect tool for us to continue evolving the framework over time without being able to make kind of bold and new changes without risking breaking existing applications. And we're really confident that our users are going to love these improvements to the Angular ecosystem. And we're working really hard to finish up Ivy and get it into your hands so we can see what you do with it. Thank you very much. I think we're a little short on time for a Q&A, but I will be hanging out just outside the theater here if anyone wants to stop by and talk about this. Cheers.